Ready? We're finishing chapter 11. Where are we going to start here? Where do we want to start? Right here? Constant service. 527, if you're trying to look at a formula, and I would. Matter of fact, I have the formula right here. You take this, and you do that. Put this here, do this. You see it? Okay. What you're looking at, the reason constant, and I think I already told you this, is only has one formula here out of the 6, is because this is the only one that's different than arbitraries. And all the rest of arbitrary and constant are the exact same. Just this one, the L sub q, which is like the second one down. So here's arbitrary, right here. But look at L sub q. Look at L sub q. That's the one that will be different. Constant doesn't have a standard deviation. Now there was a few people absent, so I want to make sure. This was like one of the most important parts of Tuesday's lecture. Exponential service with a single channel, right? And the other one was exponential service, multiple channel. Okay, this is the big deal, so you don't panic on a quiz 5 days from today. Let me start here. We're about to talk about a problem that has Poisson arrivals, but constant service. And the examples I gave you is that when you have constant service, you can recognize when you read the problem because the service is probably not being provided by a human. That's the usual situation. Because a human can't be constant every single time. So if there's a machine providing service, odds are it will say something like, and this machine provides the exact, it takes the exact amount of time or something like that for every customer. That would be constant service. So that's how you recognize it. Go straight to 527 or whatever, however you're going to have the formulas there. If you, again, you have the Excel spreadsheets. I posted some Excel spreadsheets today with formulas on them, and so you don't even have to make them. One of them I left with the maker. But you can't do multi-channel with a spreadsheet. Don't worry though, I'm not going to make you calculate those long calculations. It will just take too long. Just be prepared though for what they mean and how to recognize it. So constant service. Service is probably being provided by a machine for each customer. It takes the same amount of time every time. Arbitrary service. How do you know it's arbitrary? I kind of hear it.
Standard deviation.
There it is. Thank you. Standard deviation will be in there. It's the only one that will have a standard deviation involved in the service. And you go, okay, it's arbitrary. These should be easy to recognize. Now, if it's not constant, it's not arbitrary, odds are it's going to be exponential service. They're all Poisson arrivals. Here's the exponential. Multi-channel, you should be able to recognize because this is single channel, this is single channel, this is single channel. You're going, okay, there's no standard deviation. It's not a machine providing the service. So now you got it down to here, and you're going, okay, how many service channels? Are there 2 stations, 3 stations, 4 stations, or just one person providing service? And if it's a job applicant, maybe one or the other, but only one at a time. You know, you got to take that into consideration. It's kind of tricky. And you go, okay, there's more than one channel or one provider of the service. It's multi-channel because you already knew it wasn't these. And then this one, being the hardest one to recognize, I go, okay, it's not that, it's not that, it's not that, it must be this. That's the easiest way to get to this. Because these are so much easier to recognize than recognizing this right away. There's nothing real distinctive about it to say, oh, this must be, it's easy to recognize. Oh, this must be, oh, there's a standard deviation. Ah, there's more than one channel, it must be this. It's none of these 3. This must be it. And I gave you the page number for these. I forgot to write it up here. Here's the page number for these 2. Somebody, let's throw these up here because there were some people asking. Single channel, what was the page number? 512. And multi-channel, what was the number? 517. Now I want to say something. Multi-channel, do not rely on the PowerPoint's Excel spreadsheet. I even put out there in 2 places I think this is not correct. You lie on page 517. It's 517, 18, 19, is that true? Does that sound right? Where's the table that you would get your first probability one? Is that 517, 18, or 19? 18, so it must be 516 then, 'cause there's 3 pages involved. What's the first page of formulas? Is it 16 or 17?
It's 17 and the table's on 19.
Or 19, so this is 17 through 519.
I got that written down.
All right, this right here is page 526. You're looking at the arbitrary. This is different, and what's the other ones? I think this one might be different, or this one. These are the same as the exponential service ones we went over, but this is obviously different. There's a standard deviation involved. This is the average number of units weighted. Average number of units in the system. Why is the average number of units in the system one of the most important ones up there if you're a manager? Do you remember? It's the one you have to calculate the economic analysis. That's the one you have to do the economic analysis. You're going to be given every other number in the economic analysis, the cost of weighting, the cost per channel, how many channels there are, and that's the only thing you're not given, is that. And what might happen if you don't have this in your notes, economic analysis needs the average number of units in the system L. If you don't have that in your notes, I guarantee there's for sure an economic analysis coming up on the quiz. And this is so important, maybe something like it on the final, that the amount of time you're going to spend trying to figure out which one of these you use is going to be too much if you don't have good notes saying the average number of units in the system. Don't write just L. Don't write just the average number of units in the system. Write both of them. It's the average number of units in the system, which is variable L. Because you have some problems where it's the name of all 6 of these, and some of them where it's just the variable of all 6 of these. And you got to pick out what you need. I calculated all 4 of you. You got to know which ones to use. Okay? So L. All right. Here we go. We know these formulas. We're going to constant real quick. There it is. We go over here. Automatic car wash, coffee machine, whatever. Here we go. Okay. This mechanical pony rides at the entrance of J-Mart. That always makes me laugh. It provides a 2-minute ride for 50 cents. Children arrive with their parents, blah, blah, blah. And they're Poisson distributed at a mean of 15 per hour. Try to imagine this. About 15 kids in an hour's time, when their parents are checking out. They run over, they put the 50 cents in, they get a horse ride for 2 minutes, their parents gone, they can all leave, blah, blah, blah. Everybody picture this? What's hard about this is, what's the cost per channel? How do you calculate? Now I need my accounting people to jump in right now. How do you calculate the cost per channel? Someone said, I want to do an analysis, whether we should get a second pony. I need to know what the cost is that we spend on this pony, and I need to break it down to an hour. What is our cost per hour on this pony? And what's the first thing you got to look at, accounting majors, to try to figure out what the overall cost down to an hour is? Depreciation. What was paid for it, and how do we depreciate these? What's the life expectancy? How much is that each year? What other expenses go along with this pony? Electricity. How much of our electric bill is being used by just this pony on average? You know, and our depreciation, how much do we pay for it? How much is it going to cost to replace it or to get a second one? That's how you're going to get your cost for the economic analysis. Weighting cost, that's much harder. But the cost per channel is taking what it will cost to buy another one, how do you depreciate it, divide that by each year, then divide it by each 365 days or however many days the business is open, then divide it by however many hours it's open, and there's your cost per hour with the electricity and any other expense that goes. Maintenance, what percent of the time are your maintenance staff, those expenses that you pay them, and any tools or parts that are needed. What's the average amount we spend on this mechanical horse? And you break it down, keep dividing to get per hour, or whatever unit of time you want. You can go to per minute. That's how you get that cost, and then you can do economic analysis. In this case, they're arriving, we're receiving 50 cents. By the way, you got to take that into consideration. We got revenue of 50 cents. They're arriving at 15 per hour. We want to make these both into, how long is the ride? 2 minutes. 2 minutes is time. 15 per hour is rate. And for all these formulas, you've got to use rate. You need to convert time to rate. So if it takes 2 minutes, so our arrival, what what did it say, 15? And so our service, I need to convert to a rate, which will be what rate? Not all at once. That's right. You got to imagine, a child walking up to this pony gets a ride for 2 minutes, and we start the timer. As soon as that child gets off, another one's right on there for 2 minutes, and so on. In 60 minutes, how many kids would that take? Well, 2 minutes every one of them. 60 divided by 2 minutes is a rate of 30 kids could ride it if one was right after the other. We could get 30 kids on there in an hour. So there we have rates, 15 and 30. And we go to, let's do this one, arbitrary. Here's our arbitrary. We have all 6 of them there. Is this arbitrary? Oh, sorry. Constant.
Yeah, it is. Yeah.
Hey, I meant constant. Darn it. We don't have one for constant. All right. Do this. Well, I hate jumping into this right now, but I forgot about this. I know some of you are going to freak out because I'm jumping around, but I forgot about this. But you remember on Tuesday I said, hey, I need you guys to be able to analyze an output from crashing. Real quick, we'll go back, just because it's right here. Ready? How many units of time got crashed for this project in order to get that time down? How many units of crashing took place? I got 11. What are you don't say anything. What are you looking at? What is anybody looking at? What are you looking at on that output? To answer that question, how many units total is crashing there? That the program got written to crash to a certain amount of time, but you should be able to look at something and tell me how many units of time are being. Say it again.
The Y variable?
The Y variables, exactly. Now look at the Y variables only. The Y variables are always telling you which get crashed and by how much. So what's the total amount of time being crashed here? There you go. There you go. And what's the cost to reduce it this many units of time? How much is it going to cost for this crashing experience? Go ahead, say it. Look at it. Say it, say it. That's right. And that's the least we can get the cost to. He's looking at the objective function value. That is what this whole thing. You wrote the minimization objective function to say, okay, I'm going to have to crash this. I want to know what combination of activities will keep my cost of crashing as low as possible. And here they are. 1 unit, 3 units for, I can't see it from here. Is that D or E? E. 3 units of E, 1 unit of A, 1 unit of G, 2 units of H. It's going to cost $5,250. There could be another combination of crashing to get to this point, but either it's going to cost more than $5,250 or exactly $5,250. There is no combination that will get it lower than that. So let's just run with this, because that's as low as we're going to get. Okay, so anyway, you can analyze the output, everybody feel? In your notes, the key is what Austin said, the Y variables. If there's a question related to crashing in this, it's probably about, hey, how many units would you, which activity would have to crash the most, and how many units? Be prepared for an answer like that. And you're going to say, E, how many units? 3. You're going to go, okay, here's the crashing, 1, 3, 1, 2. Okay, the most, you'll put E is 3 units of time. It could be days, months, well, it doesn't matter. If you say whatever it says in the story, just units of time. Everybody get that? Boy, you guys are scaring me right now at this moment. Seriously, you guys, I mean, can you read this now? Yes? No?
Yes.
Okay. All right. Good. Okay, we're back. We're back on constant. We're going to do it this way. Boom. You ready? What do we got? Arrival, service. My question for you is, what's the probability a child will walk up to this pony and have to wait? Give me the math. What am I doing here? What's the probability a child's going to walk up to this pony and they're going to have to wait? Give me the math. 15 over 30 equals 0.5. 50% chance. The probability an arriving unit has to wait. I almost used the exact words, and I will do that on the quiz. I just added the word child, just to kind of fit with the story. So what's the probability then that this pony's doing nothing but sitting there and depreciating with no child on it? I heard it, I think. It says 1 minus the arrivals over service, so 1 minus 0.5 equals 50% chance. that this pony is doing nothing, a 50% chance this pony has a child on it already when a child walks up, right? And then, what do you think here? Let's do this, but for constant. Because we got to get to L. So here we go. Arrivals over service squared. Calculators, 15 over 30 is 0.5. 0.5 squared is 0.25. So my numerator is 0.25, blah, blah, blah. 2, here we go. 2 times 1 minus arrivals over service. So 1 minus 50% is 0.5. 2 times 0.5 is 1. Does that sound right? 0.25 over 1 equals 0.25. The probability, what we just calculate there, the probability, or not the probability, the number of, the number of children in the waiting line on average is a quarter of a child. Meaning there's not that much waiting. Every once in a while a child has to wait, so it ends up being about a quarter of a child. Let's take that now. We're going right, even though we're on constant, we're now sticking to the arbitrary formulas because we got to get this number right here. L sub Q, 0.25 plus arrivals over service. That's 0.5 plus, this is L sub Q plus this equals 0.75, right? 0.5 plus 0.25. 0.75 is our L. Now the story says, gotta remember here, that accounting just told us that this horse, if we were to add another channel, the cost would be $5 an hour. All right? You with me? And that if we don't have enough ponies and children are waiting a little bit too often, our cost for waiting is $3 an hour. So this is cost of waiting, this is cost per channel, and this is per hour. Per hour, arrivals are per hour, services per hour. We're all in the same interval of time. If somebody else wants to go break this down to per minute, no problem. You're going to get the exact same answer as long as you're using per minute on these also. Remember, every number involved has to be the same unit of time, and no matter if someone's using seconds, someone's using days, someone's using months, someone's using hours, you're all going to get the same correct answer as long as every number being used is the same interval of time, whether it's hours or minutes. And this is really important in arbitrary. This is where it becomes really hard to understand how every number involved is the same unit of time, either seconds or minutes or hours. So now we're going to do economic analysis. We have everything we need to figure out how much it will cost to have one pony there with the weighted cost and the cost per channel. Look at your formulas for economic analysis and tell me what number you want to use first. The cost per channel of 5 or the weighting cost of 3, it doesn't matter which order. You got to know though what comes with it because you're multiplying. What number do you want me to use? 5 or the 3? $3 is the weighting cost, so it's multiplied by what number? 0.75, which is what though? The average number of units in the system. We calculated L to be 0.75, plus the other cost, $5 an hour per channel, and how many channels are we figuring out the cost for right now? We're up one channel, just one pony right now. We get a new L if we go to 2 ponies, but we can't do, we're not going to multiple constant, but we would have a different L. But we're just evaluating one pony right now. This problem's going to say if we have one pony there, and here's your arrival, and here's your service at 30, with a $5 per channel cost, that's what it costs us for that pony being there, and $3 waiting cost. What's our overall cost per hour for this pony? We have, what is this, $2.25 plus 5, is that right? So $7.25 per hour is our total cost for everything involved with that pony. Waiting, and the cost of depreciation, the electricity, everything that goes with it. And that, we're going to now compare that to a cow. We'll have an electric cow there. It's a little different cost because we got the cow on rebate. It was in the discount. All right. Okay, you ready? That's it. telling you, it's all about you recognizing that you're reading the constant problems. And it's just, you know, if we went farther, you know, the average time. By the way, this average time, hey, hang on, what am I doing? I almost forgot. Right here's my constant. Here we go. What's the arrival rate for this point? Is it 15? What's the service? 30. Here we go. 50% chance that there's no children there, and that horse is just to cool off. 50% chance there's a child riding the horse, and another child walks up and has to wait. 0.25 is also Q, the average number of children waiting. 0.75 is L, the average number of children in the system. And that's the number you would pick. And they may not be in this order, so don't go with third one down. Understand what the word is that goes along with that and the variable and find it. But that's the one you would use, because probably the problem is going to say, and that horse costs us $5 an hour in depreciation and cost if we were to replace it, and we calculated the waiting cost to be $3 an hour. What is our total cost economic analysis for this horse? You have all the numbers you need. There's L, there's arrival, there's service, there's cost per channel, there's cost waiting, and you can get to this number. This problem, if that's exactly what was said, is not worth that many points, because it's very easy to read into this that there's a lot more to it if you think you've got to calculate that, but it's probably being given to you, and you just got to find it and recognize it. All right, so it really, this is the only math you're going to be doing is right here, just a little bit, because all the information's there. All right, keep going. Boom. Arbitrary. Arbitrary. Let me get the arbitrary formulas again. Single channel, arbitrary, our fourth and last one of the four. Don't get me wrong, we're not finished. I'm just saying it is the fourth and last one of the four. Come on, hang on. You ready? This university has a student union with with one self-serving copy machine. On the average, 12 customers per hour arrive. Here we go. I'll write this one down. We have 12 arriving, and follows place on. The time to copy documents follows a normal distribution with a mean of 2.5 minutes and a standard deviation of 30 seconds. 2.5 minutes and 30 seconds. Wow. We have a rate thrown at us, we've got time in minutes, and we got time in seconds being thrown at us. So we got some work ahead of us. And one person may say, I'm turning this whole thing into minutes, or I'm turning this whole thing into hours, and you're both going to get the right answer as long as you both made every number in the same interval of time of whatever it is you choose. All right, let's try hours, since we get to this, because this arrival is already in hour, right? So 2.5 minutes, you ready? There's 60 minutes in an hour. If a student was walking up to the copy machine every 2.5 minutes, we would get, is it 12, 15, something like that? What's 60 divided by 2.5, 24? 24, thank you. So we just turned 2.5 minutes into a rate of 24 per hour. And the standard deviation is 30 seconds. You do not turn standard deviation into a rate. Well, I better tell you that right now. Because I just realized this is the only thing you don't turn into a rate. This stays in time. We got it? The standard deviation's in time, but the time has to be in the same units that you're using for the arrival and service. So we're not using seconds in the arrival and the service, we're using hours. And it says 30 seconds. If we were using minutes, this would be easy. This would be 0.5, a half a minute. But this has to represent how many hours the standard deviation is. So I gotta think about that. Hang on. Where's my calculator? Right here? Hang on, I'm getting a real calculator out. I don't know what that means. What did I say? 30 seconds into hours? Anybody have an answer? I just want to, because I think I know. Anybody have an answer? Well, you gotta give me a decimal. 0.0088. That is it. It's what you do is you say there are. Let's see, how do I do this? 30 seconds is 0.5 of a minute. So, yeah. So what is it? What divided by what?
It's be 0.5
What?
by 60.
Divided by 60. And I was just thinking that this is one divided by 120. But 0.5, because it's a half a minute, there are divided by 60 minutes in an hour. So that's 0.0083333 of an hour. So now we have this in hours. This is in hours, that's in hours. This is gone. And now we can answer any of these questions. We can do any of these formulas. This will take a little bit of time if you had to do it. Probably won't, but if you had to. Now you can do that standard deviation as, where is it? Gyration? 0.00833333 would be that standard deviation, that second little variable there on the top, to the right, from left to right. Arrival square, standard deviation squared, plus arrival over service squared. The denominator, 2 times 1 minus arrival over service. Or you can open up that spreadsheet I posted. And right here is asking you arrival rate per hour in this case, 12. Service rate per hour in this case, 24. Is that right? And standard deviation in hours, 0.0, another 0, 83333 right there. Okay. What's the probability that a student walking up to that copy machine is going to end up having to wait? Okay. Anybody else? Because I know they didn't hear you. I heard it. Say it again. I heard it coming from somewhere. Well, what is 0.26? That would be the average number of units in the waiting line, but the probability, I was asking for the probability that a student is going to have to wait when they walk up to it, 50% chance. What's the probability that that machine is not helping any students at all because there isn't anybody needing anything copied? 50% chance. Okay, now, what's the average number, when students do have to wait, what is the average number of waiting per hour on average? Now, 0.26, just a little over a quarter, which is pretty low compared to the pony. It's almost the exact same, right? They were about 0.25. And the average number of units in the system is 0.67. Look at this. Average time a unit spends in the waiting. This is average time. What is that? 0.0216666 what? Hours. Because the arrival was hours, the service was in hours, and the standard deviation was in hours. These time ones are in hours. But the question's going to say, how many minutes? What is that? Wow. How many minutes on average does a student spend in the waiting line if they have to wait? 0.02, so you take 0.021, is that 6 right after? Yep. 66666 times what? Because that's how many hours. I want how many minutes? 60 minutes. That will equal the amount of minutes that that number represents.
1.3.
Thank you. 1.3 minutes. Okay. How many minutes is the average time a student will spend in the system between waiting and having their copies made if they have to wait or whatever? The average time. This would be 0.06333 times 60 minutes, because that's an hour, equals 3.79. Oh, so that's 3.8. 3.8 minutes. Hang on, I'll look at something real quick. I think this may be one of the questions here. Is that up? What's the average time a customer must wait in line before using the copier? The average amount of time is 1.3 minutes. We got right here, and it doesn't go to the next one, huh? The probability that the copier will be idle and no students are there to use it, 50%. The probability that the copier, that a student walks up to make copies and they're going to have to wait, 50%. Okay, let's add the story. We found out that that copier is costing us about $7 per hour, and we We think that if it's, you know, I don't know if they have to pay to make these copies, but we found the waiting cost to be pretty low, about $2 per hour. Let's do the economic analysis. Are you ready? What do we want to start with? The waiting cost or the cost per channel? Can't hear you. It's the $7? $7 is the cost. Is this, let's see, this is waiting, so this is the cost per channel. So $7 times K, which is the number of copy machines in this problem, which is one copy machine, plus the waiting cost, $2, times what? Times, let me get the PowerPoint out of the way, maybe that helps. Times what?
How long do you have to wait?
Not how long they have to wait. Was that Nick? Thank you, Nick. Was that Nick?
Yeah.
Thank you. Anyways, you're jumping in, and I appreciate it. Say it again. The average number of units in the system, which is what variable? L, and it happens to be how much? 0.76. 2 times 0.76 equals 1.52 plus 7, $8.52. Someone help me and tell me if that's right or wrong.
That's right.
$8.52 is our total cost for that copy machine based on our arrival rate, our service rate, our standard deviation, the cost per channel, and the cost for waiting, all in the same units. I want to make sure you get this. Are you ready? We're going to minutes. Real quick. We're going to minutes. 12 per hour is how many per minute? This is 12 per 60 minutes is equal to how many per 1 minute? 12 times 1 divided by 60. 12 divided by 60 is 0.2. 0.2 per minute is our arrival now. 24 per hour. 24 per 60 minutes is how many per 1 minute? Cross multiply, 1 times 24 divided by 60 is 0.3. No. 24 divided by 60 is 24 divided by 60. 0.4. 0.4 per minute. There we go. We got a 0.2 arrival, 0.4 per minute. Our standard deviation has to be in minutes. 30 seconds is how many minutes? 0.5 minutes, a half a minute. There's our standard deviation in minutes, our service in minutes, our arrival in minutes. Uh-oh. $7 per hour channel needs to be per minute. $7 divided by what? 60 is how much per minute? 7 divided by 60 is 0.116 repeating per minute. Now our $2 per hour, this will be a small number. 2 divided by 60, 1 divided by 30, either way, equals 0.03? Really, there's not another zero? Oh, wow. 0.03 per minute is everything in minutes now. Are you ready? Okay, remember this. What was L? 0.76. Watch, I'm going to blow this. All right? This isn't going to work. Try to be embarrassed. Here we go. What was our arrival again? 0.2. Service, 0.4. Standard deviation, 0.5 minutes. Is that right? Look at this. Same exact answers. Everything's the same. Let's get our total cost per minute.
Okay, you lost me. Service started at 2.5 minutes.
That's right.
And
but
then
that's
convert it-
time and not a rate. We had to convert it to how many
Okay.
instead of how much. So we took 60 minutes divided by 2.5 and got 24 per hour.
And then we provided the, okay.
Now we have to take this and break it down to per minute. Still as a rate though. We could take this per minute, and this would be, if we can help one customer in 2.5 minutes, how many customers in 1 minute? We can't even help one whole customer, so it'd be 1 divided by 2.5. What's 1 divided by 2.5? It should be 0.4, is that correct? It is? So we would take 1 divided by 2.5. In this case, if we wanted to go straight to per minutes and avoid the hour altogether. But anytime you're given time for service or arrival, you've got to convert it to rate. Instead of how long this is going to take, it's how many in an amount of time. You've got to switch it to do any of these. Got to be in rate. And you will have a problem with numbers in it. Look at all the numbers are the same. Just real quick, we would use, where's our cost per channel now? 11.6 cents times 1 plus 3 cents, 3.3 cents times 0.76 is the same now, right? Nothing changed. And then that would be Matter of fact, I could get the answer just taking this per hour cost and divide by 60. It's the same, everything's the exact same, but now we just found the total cost per minute instead of per hour. And if you want to change this all to per day, well, hey, this business is 8-hour day. You take everything, multiply it times 8, use day for everything. I hope everybody at least got this out of that, all of this we just did just now, is that all of these numbers have to be in the same unit of time. That's the number one mistake I see on these quizzes. All right, same units of time. And standard deviation stays as a time instead of converting it to a rate. Don't change that to a rate. Standard deviation stays time. Now, wait a minute, forgot. Oh yeah, we're going right here. Is that showing up? It's not on my screen. There we go. Number 10, you see number 10 real quick? Are you ready? I want you to hear this problem, and I want you to start thinking to yourself, which one of these 4 is this? All right? It'll jump out at you pretty quick, hopefully. You know, you're starting to look for certain things so you can quickly identify which one of these 4 is number 10. This tire company decided to hire a new mechanic to handle all tire changes for the customers ordering a new set of tires. 2 mechanics applied for the job. 1 mechanic has limited experience, can be hired for $14 an hour, and can service at an average of 3 customers per hour. That's a rate. I thought it was going to give us time there. I was surprised. 3 customers per hour. The other mechanic has several years' experience and can service the average of 4 customers per hour, but it's got to be paid $20 an hour. Assume the customers are arriving at a rate of 2 per hour. Which one of these? Just give me the service part. Exponential what? Single channel. There's 2 applicants. This is very much like that problem I kind of showed you 2 days ago, but only one of them's getting the job, and they both demonstrated how long it would take them on average to do the job. So that would be single channel, exponential, page 512. Look at the 6 operating things that we're calculating. Maybe you're given the numbers. Maybe you have to calculate just one of those this problem has, something like that. Let's go to, here we go, 27. What we're doing right now is what most students find the hardest part about this quiz that slows them down. I don't know which formulas to use. So that's what we're doing right now. I'm getting you past that. Because once you're past that, you turn to the right page, you know, it's just a matter of plugging the numbers in, if you even have to plug numbers in. Just recognizing which numbers to use. Number 27 says, the welding company operates a welding service for construction and automobile repair jobs. Assume that the arrival of jobs in this company office can be described by a Poisson probability distribution arriving at 2 jobs per 8-hour day. This is the first one we've seen in days. We could break it up to hours though by, you know, this is, does it say 2 jobs per 8-hour day? The time required to complete the job follows a normal probability distribution with a mean of 3.2 hours, that's in time, not rate, so be careful, with a standard deviation of 2 hours. Which one are we using? All right. I heard you. You said arbitrary, like all at one time. Thank you. And you recognize because you saw the standard deviation? Help me with the service. Let me look at it first. Service is not 3.2 hours because we're going to calculate this. We got to divide 3.2 by what? Or what? I'm sorry, what divided by 3.2? 60, because that's 3.2 hours. There's really 3.2 hours? What am I talking about? 60. Are we going per day? What? 2 per day. So let's go. Hang on now. This is tough. Ready? Let's go over here off camera. 2 per day is our arrival. And if we leave this as day, we got to convert to day for everything. So if this is 2 per day arrival, and we'll do this for now as that, 3.2 hours. The day is 8 hours. 8 hours divided by 3.2 is 2.5. So our service is 2.5 per day. Here we go. Now we have our arrival in a rate. It was given to us. We converted service to a rate because it was given to us in time. Standard deviation now, to keep it in time, but it's got to be based on days. So if it says 2 hours, look at what a day is, 8 hours. What percent of 8 hours, or how do I describe 2 hours, but it's what of 8 hours? So you're pretty much saying 2 hours is what percent of 8 hours. fourth of it. So that would be 0.25 hours, I'm sorry, days, because that represents 8 hours for our standard deviation. You can solve any of these now. You go to the arbitrary formulas if you even need them, and you can solve any of these quickly, because these are the three numbers you use, and they're all in the same. Let's go to hours now. Is that what you're going to say? Go ahead.
You said you were going to give us some of them, like on the quiz, like we aren't going to have to calculate them.
That's
So
right.
how would we be able to tell the difference if you just give us a bunch of numbers?
I don't want to give it away yet because that's your inconsistent.
Okay.
You're going to see exactly how to do it. You have to do it.
Okay.
It's where I'm okay, I'm giving it away. It's where I'm literally going to give you all 6 numbers.
Okay.
And either they're going to have their variable names with them or the names themselves, and you got to figure out which ones to use.
Okay.
And you'll be given this information, and you most likely will have to convert 1 or 2 of these, so they're all the same units of time. Let's go with hours. We're going to switch this to hours, just so you can see how you can get the right answer, even with completely different units of time. It says 2 jobs every 8 hours. I got to think about this. 2 jobs every 8 hours. 8 hours is a day, right? So it's 2 over 8 is something over 1 hour. So 1 times 2 is 2, divided by 8. 2 divided by 8 is 0.25 per hour is our arrival. Help me out. Anybody get the same answer?
Yes.
Okay. Service now is given to us in time as 3.2 hours, which we converted to 2.5 per 8 hours. We want this to be how many per hour? 1 times 2.5 is 2.5 divided by 8 equals 0.4? 3125 per hour. So we converted the time, we already converted it to per day right here, which we knew was 8-hour day. And we took the rate for an 8-hour day and converted it to what would it be then for a 1-hour day. We took how many on the arrivals per 8-hour day, because it's per day, and we converted it to a 1 hour. So now we have 0.25 per hour, 0.3125 per hour, and the standard deviation is 0.25 days. Whatever 0.25 times 8 hours would be turning it to hours, or up here it says standard deviation is 2 hours. It's literally being given to us as hours, so the standard deviation would go to 2 hours. So this is in hours, hours, hours. You'll get the exact same answer if you were using day, day, day. Same right answer. That's the hardest part. Now you just plug the variables in, right? I guess it looks like, what do you do from here? Well, so I'm going to show you how easy it is to go from here. I can't remember the story. This is tires? What's the probability a car coming to get their tires done, the person who does, I forgot what the person's even doing. Are they rotating them? Welding them?
This is welding.
Oh, dude, I don't even have it up. Shoot. Welding. God, that was tires. That was the last problem, huh? Okay, here we go. What's the probability that a job comes to be welded? Is that what it is? Has to wait. You ever hear that? The job, the probability, that's the key word. There's only 2 of them that have probabilities. 2 of them are average time. 2 of them are average number. So the word says, what's the probability a job comes for the welding service and has to wait? So we're looking at this now right here. And this would be arrival over service, which is 2 over 2.5, which will be the exact same answer as 0.25 over 0.3125. And that happens to be 80% chance? 80% chance that a job coming for welding is going to have to wait. What's the probability that the welder has nothing to do, that there's no jobs available? Say it again? That's right, the opposite, 20% chance. You're getting this. You got it. And if I'm asking for economic analysis, you're probably going to be given all 5 numbers. What was it? This is arbitrary? You ready? Well, what's the arrival, either per day or per hour? Just give me the numbers in the same category of time. What's the arrival in, what is it?
2 per day.
2 per day. And then the service is how many per day? 2.5? 2.5, is that correct?
Correct.
And then the per day for 0.25 is the standard deviation. Okay, what's the probability, what's the average amount of time that if a welding job has to wait, what's the average amount of time it will be waiting? Okay, so which variable are you looking at? The average amount of time a job would have to wait if it has to wait. Which variable? WA. Average time a unit spends waiting. So here we go, 1.1125. What? 1.1125 what? Days. Because we use the days arrival, service, and standard deviation. So this is 1.125 days, but the question says how many hours? What do I have to multiply that by? Because there's 8 hours in the day represents 8 hours. 1.125 times 8 equals 8.9 hours a day, and 9/10 of an hour, which would be, 7.2 hours, right? Additional hours. Is that right? 54 additional minutes on top of the 8 hours. So almost 9 hours would be the average waiting time. See what I did though? These times are being given to you whatever the unit of time was that these were converted to. But the question may be in a different unit of time. Now, real quick, if we would have used per minute, and minutes here, then this would be in minutes. This would be how many minutes? What is the minutes on the arrival, just to show you? Point what? Point what? 0.25. Service then is point 3 what? 3125. And this was 2 then, 2 hours? Okay. How many minutes does the average welding job have to wait if they do have to wait? And here it is, average time the unit spends waiting, exactly what we calculated when we were using days, 8.9 hours. And this is already in hours because we used hours up there. This is crazy stuff. Here's one for you. If you're worried about your welding business providing satisfactory customer service, and you don't want them to go to your competitor, do you think that your particular process you have right now is efficient enough to take that worry away? Katrina says no. Anybody else? Katrina says no. I'm sorry. No, no. What are you looking at? What are you looking at?
It's just taking longer than a day to even.
You're looking at the average amount of time because it's taking longer than a day waiting even, right?
Yeah.
They may take that somewhere else. What were you looking at? The average time waiting? Average time waiting? I look at, anybody else look at something else? I happen to look at the probability that a job's going to have to wait. And if there's an 80% chance that a job's going to have to wait, that's like just saying we're planning on someone waiting. And that's not the best customer service depending on the scenario. And if you're worried about it, how do we bring this down? What could affect that? If we can't affect the amount of time we're averaging on providing service, what's another way to affect that probability? Add another channel. That's right. We need to have another station that's doing this welding because we're busy enough and we're not providing the best customer service and we don't want to lose these jobs to our competitors. And this is telling us, and that's telling us, and so on. In real life, that is how you're using this information. On the quiz, I'm only going to maybe ask you one of these or two. You may only if I'm asking you to calculate anything, it's just maybe one of these, not all 6 in any way. And then the next question may give you all these, and you've got to answer something about that and analyzing what you see. Okay? All right. All right. We're going to problem 9. Marty's barbershop has one barber. Okay, that takes care of multiple channels. Has one barber. Customers are arriving at a rate of 2.2 customers per hour. That's it, 2.2 per hour. For haircuts, given the service rate of 5 per hour. Any conversion on those at all? No, they're both rates. That was pretty lucky. Use Poisson arrival, exponential service, following equation. Which one is it? Which service do you have there? Can you give it away a little bit? Actually, no. That barber cuts hair at different times. If it were a robot barber, and that's our future. When you do that, that's our future. Robot barbers. or bowls with a air master. I don't know. Whatever it's called, I'm sorry. This is exponential service single channel. Single channel. You jump into page 512, easiest formulas there. I'm probably asking you to calculate something instead of giving you the numbers because page 512 is like the easiest calculations of all of them, right? I mean, even the average number of units waiting will take you only a matter of a minute to calculate because you've got the arrivals, you've got the service, you don't even have to convert them. It's just knowing which ones to use. Okay? Do you guys want me to post the pictures I've made of these key pages with the formulas on Blackboard? Okay. All right. All right. Let's look at another one. We just got a couple more and we're out of here. And the reason these that we're talking about right now are important because I think I've already posted several answers to problems for you to use to study from. And these are the ones that we're talking about right now, the answers I posted. So have you recognize it, kind of give you a lead here. Let's go to number 18. Am I accurate? Yeah, I am. All airplane passengers at the Lake City Regional Airport must pass through a security screen. This is a common one. Security screens where they should have a second or third station. I hear about these a lot. The airport has 3 screening stations, and the facility manager must decide how many of them to open. The service rate for processing passengers at each screening station is 3 passengers per minute. Does that need to be converted? Oh, does that need to be converted? No, 3 per minute is a rate. If it said it takes 3 minutes to do a passenger, then that's a time, and that would have to be converted. But this says 3 per, I lost it, minute, thank you. What number was it? 18. Thank you. The service rate processing each screening station is 3 passengers per minute. On Monday morning, the arrival rate is 5.4 passengers per minute, assuming the process time follows blah, 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 blah. Which one is this? Just give me the service that it is. I can't hear you. No, it's not constant. There's a human doing the screening. Even though the station does have a machine involved, there's a human involved, and it can't be constant. What is it? Exponential what? Multi-channel, because it could be, well actually your first analysis, if we did all this, would be, should we open 1 station, and we would use single channel. Then you use 2 stations, using multiple channel, then we would do 3 stations. If we read on, it will say how many of these stations have to be open to keep, maybe it will say something like to keep your probability of a passenger having to wait down under 50% or something. So you're doing all of these to get that last number, probability of a unit has to wait, in which one of them will get you down below that 50%. All right. Here we go. I lost it. Did I close it? Yeah. Closed it. Hang on. Fitting? Is this up on screen?
No.
Okay, good. Okay. Let's talk about one. Let's do this last one on the software. For those who can see number 27, you don't have a book? All right. Gubs or whatever. Did we read this one already?
Yes.
How come I have 27 on here twice? Okay, let's go back to 18. All right, 18. What was the arrival rate on 18? 3 passengers per minute, 5.4 passengers per minute, and it was, and here we go, ready? Your software has a module called waiting line, right there. You click on waiting line, hit OK, you go File, New, and it comes up like this. All right, are you ready? You have to write a little note here because Poisson arrival exponential service, this is the one you use. If it's single channel or multi-channel, does not matter, that's the one you use. Let me repeat that. Exponential service, single channel or multi-channel, that's the one you use. The second one down, arbitrary service, 1 channel. There's the arbitrary service, single channel. Do not accidentally use arbitrary service, no waiting. We're not covering this one in this class. That second one down, arbitrary service, one channel for arbitrary. So we got two exponentials, single, multiple, arbitrary. Deterministic service means constant service. So you don't have the word constant there, and I get this in the middle of the test or whatever, or homework, I can't find constant. Deterministic is the same as constant. So, and you're not using the bottom one. Either one of these two. This one, this one, this one. And this airport is, we determined it was what kind of service? Exponential? And how many channels? Oh, single? All that. So we'll go here. Here we go. Arrivals are 3 per minute. Is that correct? Right? Service is, how much service?
The first one should.
Oh, number of channels, sorry. Hang on. 1. And the arrival rate is 3. The service rate is 5.1. Help me
I
out.
thought the service rate was 3.
Oh, is it? Let me look in. Says, service rate, thank you, professors. Where's your arrival? Monday morning arrival rate, 5.4. Okay, I got them backwards. 5.4 arrival, 3 service. Now, this is going to come up unsolvable. Do you know why? If you have passed, I'll take that back. It won't be. Just take a look. What did I just hit? Ah, here we go. Let's see. Says the arrival rate must be less than 3, or the waiting line will grow without limit. Meaning, if they're arriving faster than a single channel can provide any service at all, there's no way this can be solved. Because you are literally have a waiting line almost right away. And this is per minute, by the way. So there is no way we can use a single channel. Can we use 2 channels? Now, do not change this to a 6. I see this every semester. You're just changing the channels. This always represents the service per each channel. So we put 2 channels in, which, by the way, 2 times 3 would be 6. So now we have a service being provided more than arrivals, which means this can be solved. Right there. What's the probability that a passenger is going to have to wait when they go to screening? 85%? This is not the Secretary of State. We are not going to deal with 85%. Matter of fact, I don't remember if there's a cost involved. We should have run economic analysis, but let's edit this. Here we go. Let's see what happens if we open all 3 channels. And we're able to lower that probability of providing better customer service. And yeah, line's going to form, but now the probability a customer is going to have to wait when they come to catch their plane is what? About 35.5%, 36% chance, right? Not bad. What's the probability the staff with all 3 of them open are going to have to twiddle their thumbs and do nothing, and we're paying all of these people for nothing? Yeah, it's only about, the probability is only about a little less than 15% chance. That's okay, that's not bad. They're 85% of the time, they're busy. So this isn't bad. Now you remember, in real life, you're doing this for an interval of time that you have this constant arrival rate happening. And that may be only like a 3-hour shift. You then say, oh, our arrivals in the next 3 hours on average is a little less. That's our busy time. And you redo this so you know exactly how many stations to open when your arrivals are a little less. And do it again. And that next shift, our arrivals pick up again. We have flights in the morning or whatever this is. We have flights at night. We pick up again. It's even more than 5.4. You do it again in real life. And that's how you come up with how the minimum amount of employees, the minimum amount of stations, whatever you're doing this waiting line system for, that's how you get those minimums. Then you switch over to linear programming, write that objective function constraints, just like that problem I talked about on Tuesday. And that's how you then come up with your schedule. This comes up with the minimum you're going to have for each shift. The linear programming puts the exact schedule together, how many you have started this time, how many at that time, how many at that time, so that you have it all covered, all the minimums covered. This is what's done in real life. If anybody's ever worked at a bank or credit union, always, every class, I have at least one person. Nobody's ever worked, anybody who ever worked at a bank or credit union, you have. The tellers, if they're big enough, are being scheduled exactly like this. That's exactly how it works. They have every transaction that happens at bank or credit union has the time, has everything on there. How many customers have arrived, how long it took for them to have service, They have cameras everywhere. This is exactly how they come up with it. And they know what times they're busy on Mondays, what times they're busy on Tuesdays, Wednesdays, and they put a schedule together this way. And they just plug in the different arrivals, service, you know, and whatever else they need. Basically, it's arrival and service, and they can come up with the schedules to minimize the cost of employees. That is it, except for your in-class. Let's go.